Hello, we're going to try another problem with friction on a level surface, but I am actually just changed this problem. Instead to look for a numerical answer, we're going to try to find a more qualitative conclusion. Okay, will the crate actually move or not when it weighs a certain amount and a certain amount of force is being applied to it, and you're given both the coefficients of static friction and kinetic friction, and will it move at all when being pulled on the side like so. Okay, so we're already given the free body diagram in this case. It's on a level surface, so the normal force is just equal to the weight which we're given, and it's just being pulled at a straight angle, 0 degrees, and so it's fairly simple. But we're going to try to see if it will move or not. Actually, this is two problems in one. I'm just going to combine them, and you're going to see what happens. Okay, will it move? So we're given the weight, the magnitude, at least, and also the magnitude of the applied force, 12 newtons. We're also given coefficients of static friction and kinetic friction for this crate to this specific floor. We don't know what it is, but these are given to us, what the floor is made of or what the crate's made of. We're not concerned with that. Our goal is simply to find if there's any acceleration at all. Really, is there going to be any movement? So is there going to be any velocity? Is there going to be any acceleration? And you'll find out. There we go. Our formulas. We'll need the formulas for friction. Static friction, as a matter of fact, is actually an inequality. Or you can write down that the maximum of the static friction is equal to mu s n. Otherwise, it's going to be less than that. Kinetic friction only has one value, though. It levels off. And we're also going to need just one little snippet here of Newton's first law. Okay? And that's pretty much it. So the reason why we need this, because there's no acceleration in the vertical direction, or nor movement for that matter. And as you can see, normal force is going up, weight's going down. And that's pretty much it. I like to use capital N and then minus Fg in this case. So if I add that to both sides, this actually proves that the normal force, the magnitude of the normal force at least, is equal to the magnitude of the weight. That allows you to substitute it for the friction formulas. Okay, and here's our clincher, is the applied force, is this going to be greater or equal to the maximum of the static? And let's find out. Let's work with the maximum of the static, because this is actually equal to, let's write it here, 0.5 times the weight, which now we know is simply 40 newtons. And so that's just actually half of 40, which is very easily 20 newtons. But let's bring this down here. but this is only a measly 12 newtons. Now, is this greater or equal to that? That is definitely not true. Okay, so when that happens, the force of static friction will simply match whatever the applied is, since it is a linear function. Because remember, it's either less than or equal to USN, and so in this case we're talking about the less than, okay, which would result in the 12 newtons. So there will be no movement. So the conclusion here is that there's no velocity, there is no acceleration, and there is no movement. Okay, and that is our answer. So let's change things up a bit. We're actually not done yet, because we're going to do another problem, exactly the same thing, only one thing has changed. That 24 newtons. Now the same exact given, so wait, this is completely wrong. So we're going to ask the same question: will it move? And you could probably guess what's going to happen here. So now the only thing, the given is pretty much the same, but now the applied force is twice as much, 24 newtons. So is the applied force, is this greater than or equal to the maximum of the static? And we already know what this is. It's 20 newtons, and the new applied force is 24, and sure enough, 24 newtons, and sure enough, it is absolutely greater. Okay, so that means there will be acceleration, there will be velocity is actually going to increase by certain acceleration. Acceleration is going to have certain sort of constant value, and it will move. Oh yeah, and let's find out how much friction that is. So really quickly, and this just transitioned now to kinetic friction, believe it or not. So the kinetic friction is mu k n. So that is going to be 0.4 times the 40 newtons. And so that's going to result in 16 newtons. So it's going to have a net force of 8 newtons that's going to accelerate it. Okay. Now it kind of went a little bit different here. It's our F net. And I even forgot for this one, we also have a static. But in this case, the kinetic friction is going to be smaller. Cute. Look at that. And the F net is going to be F applied. I apologize for that mishap. Fk. So that's going to be 24 newtons minus 16 newtons. So it's going to, the net force is positive 8 newtons to the right. Okay, and you can solve for the acceleration, solve for the velocity later on. I think that is enough. We're going to stick with our conclusion right here that it will definitely move. Okay, cool. I hope that clarifies a certain thing. Make sure don't forget the friction like I did in your free body diagram, since this is not a frictionless surface anymore. Okay, hope this gave you a better understanding of the differences between static and kinetic friction, and I hope you learned a little bit more on how to solve problems like these. Good luck and enjoy.